always misused, right? So we have samples that we're going to test. Besides the samples we had yesterday, or last week, we're going to do some Brunel on those samples. And you guys are actually going to read the Brunels. You get to see how hard it is to do a hardness test the old way. These are small samples of stainless steel, and that's a thin sample of stainless steel.
I hate stainless steel. It's so hard to cut.
And why is that?
Because it's stainless steel. It's one of the hardest steels there is.
Well, here's what we're going to get. You guys are going to need to take this on. There are some terms. And stainless steel, the type of material it's called, the term and why it's hard to cut is because it's austenitic. Austenite. Okay? It's austenite at room temperature. That's why it doesn't like to be cut. It's very soft and very gummy. Hence is also why it's not magnetic. It's a totally different phase at room temperature than regular steel is. Okay? So, we'll go back to YouTube and that iron to carbon diagram, and we'll tell you how it's so weird and why it changes. Okay, this is the diagram for steel. Basically, it's showing carbon content. We deal with it up to here, up to 2% carbon. Everything else is iron. That's why it's magnetic, right? This is the austenite range. This whole diagram gets completely distorted for stainless steel because you're adding 18% chromium. Chromium. That's what makes stainless steel stainless steel. 18% chrome, 8 nickel. Whole different alloy than all the other alloys I showed you. I showed you all the different steel alloys. The most common stainless steel is called an 18-8. 18% chrome, 8% nickel, and you don't like machining it because it's got 18% chrome and 8% nickel. It doesn't have all iron with nice little chip breakers in it. It has all this alloy in it. A lot of alloy. This is a very expensive material. Very expensive. As a side note, chromium is not found in North America. So you wonder why we have trade agreements with Africa and South America, because they have deposits of chromium that we buy.
Is it radioactive? No?
Chromium is just
It's a mineral too?
it's a pure element of chromium. It's on the periodic chart. It's called Cr, capital Cr, chromium. So corrosion resistant steels are very cool, but they don't like to be machined at all. Because this whole phase here has been shifted to room temperature. That austenite range is at room temperature. Okay? And that's why it's like to be machined, because it is stable at room temperature because of 18% chromium. That's how it works. It's another whole metallurgy separate from steel. It's just people that know stainless steel don't know steel. I mean, it's a whole different animal.
But in the regular steel, like the 4140 for instance, when we did heat it up to the austenite state, and then if we didn't quench it and temper it, then we risk the steel being brittle, right?
No. If you cooled it slowly, it'd go back to the way you started. So the speed of how, remember that TTT curve? You go slowly through the TTT curve, and you get what you started with. Something similar.
It's brittle when it's hot. Right?
Well, it depends on the rate of cooling. If you cool it slow, it's just as soft as...
But I'm saying once you have it heated up, that's when it's brittle.
Well, it's brittle when you heat it up and quench it and don't temper it. So the quench and temper is two phases. The quenching cycle, which makes it hard, and then the baking or tempering cycle, which restores ductility. But if you don't do that, it's soft.
So the steel that is being constantly in room temperature in the austenite state may be very potent to lose its values under certain lower temperature.
This stainless steel?
No, yeah.
No, stainless steel. This whole diagram, and I have to find you an 18% chromium diagram. You don't want to see it. It's an ugly diagram. I spent the whole semester dealing with these diagrams, and it's called, this is a binary, this is a two-phase diagram. It's iron and carbon, right? I'm sorry. Yeah, it's an iron-carbon diagram. I had a class called ternary phase diagrams, which has 3 different main components. So this would have carbon, chromium, and nickel.
So it's like
And it's in 3-dimensional.
three-dimensional.
It's 3-dimensional, so you have to do this in 3 dimensions to know what temperature you're at and what's going to occur. Let me tell you that this phase, this austenite phase, is suppressed way down to room temperature. And that's why it's actually called an austenitic stainless steel. All right? Believe it or not, there are other stainless steels that are lower nickel contents and lower chromium contents that are called martensitic stainless steels. And because you've played with the chemistry, now you can quench and temper them. Let's go to the next table. The next table is for nickel. Same scale, nickel materials. There's a whole metallurgy for nickel. Nickel is what goes into jet engines. Nickel can stay hard at 1700 degrees Fahrenheit. That's how jet engines work. That's how it does it. It's actually called Inconel. Inconel is a trade name.
What about tungsten? Can't it stay hard at even higher temperatures?
Tungsten is hard to work, and it doesn't stay hard. It stays as tungsten, but it can't get as hard as nickel. Tungsten also has a whole different thing with its density. So tungsten has specific uses, but not for making high-pressure turbine discs, which compress the air in a jet engine. So at the end of the jet engine, you have thrust. I worked for 6 months for General Electric when they were building their jet engines in Milwaukee, and everything was Inconel. So everything is made out of this high-temperature material. It's very expensive. But this is a nickel chart. Same chart. How to convert what to what. You can't use the chart I showed you last week. So now, each chart only has certain scales on it because it only gives certain scales apply. Okay? So nickel is typically so soft, they don't bother with Rockwell C. All they have is the Rockwell B scale, Vickers, Rockwell B, and all these soft T scales that we're going to deal with today. Last week we didn't discuss them, but today we're going to discuss them. These are what's called, and you need to know this, superficial hardness testing. Superficial, in the old days, there was a specific machine called a superficial Rockwell machine, and it only did these 3 scales. 15T, 30T, and 45T. Basically, it's the Rockwell B indenter, but the Rockwell B indenter
15 what?
T.
15, 30.
Read the time. 15, 30, and 45 T. Those are the scales that are the softer. These are the equivalent of the Rockwell B because we're on the same page. But Rockwell B is 100 kilograms. These are 15, 30, and 45. These are what's called superficial, hence the word superficial, meaning just on the surface. These are for thin things like this. You can't put a Rockwell B indenter on something like this. It'll punch through it, and I'll show you how. So that's part of hardness testing is applying the proper load or the scale to what you have to test. You can't put a Rockwell B on that. You won't get a convertible number. So there's a whole, and they actually categorize it for you right here. Rockwell superficial hardness number, these 3. Back before combination machines, you had to have one machine that maxed out at 45 kilograms. You had another machine that did Rockwell B and Rockwell C like we did last week. So those digital machines that I have actually does both. Actually does both.